All right, so we're plugging away through heat exchangers. I hope we've covered pretty much the theory. It's now just application. And I hope you brought your clickers today, because I do want to use clickers today. And so let's jump into it. Here's a problem. You may want to get out a piece of paper, make a sketch on this, make some notes or something. But we have a very long counterflow concentric tube heat exchanger. So all those words matter. It's very long. It's counterflow. It's concentric tube. It's heat exchanger. And then they tell you that we have a hot fluid coming in at 120 degrees C, cold fluid coming in at 30 degrees C, and the specific heats of the fluids are the same. So it's probably water, just hot water and cold water. Okay, so the specific heats are the same. If the mass flow rate of the hot fluid is twice the cold fluid mass flow rate, what will the hot fluid outlet temperature be? Will it be 30, 60, 75, 90, 120? And I'm going to give you enough time to actually work on this and then put your answer in. But let's start here. All right, so I would encourage you to make a sketch when you try to work through these things. So I know that I've made a really simple plot like this or sketch like this when I have concentric tube. And then maybe I put the hot on the top and I put the cold in the bottom. I've seen some more people put kind of three-dimensional rotated view of a pipe inside of a pipe, and that's nice. But this conveys the right information. Then we put the information in that the temperature hot in was 120 degrees C, and the temperature, whoops, wrong direction on that, isn't it? Temperature cold in is 30 degrees C. Then I also recommend you make a plot, and this will be a function of X. But the L is so large that you sometimes put this in the illustration. What's that? Showing its break. It's so long. So we'll put a break in it right here so that it's so long. So now the temperature here, we'll put the temperature hot in, 120. Down here is 30. You might even want to do, there's 30, 60, 90, 120. So this is 60. And that's 90. True? 30, 60. Kind of get it to scale on the temperature. And way over here, we're coming in at 30. And right here, we're coming in at 120. Now, somebody says, what does the plot look like for a finite length? It'd be something, this is going down and this is going up, right? Maybe, as I mentioned when I walked around the room, maybe I should have started by saying that the mass flow rate of the hot fluid is equal to the mass flow rate of the cold fluid. I think that would have been a little easier, right? What would that plot have looked like? Wouldn't it have looked like the hot starting here, and then because it's so long, it actually goes out at the cold, and the cold so long that it actually goes out at the hot? It's like infinitely long. Would that not be the right case if it's infinitely long? So very, very long counterflow would look like that. But what did we do to the mass flow rate of the hot fluid? It's twice the mass flow rate of the cold fluid. So if I take this sentence right here and I put it in equation format, is that saying, clicker question, m dot h is equal to 1/2 of m dot c, or m dot h is equal to 2 m dot c? Either answer A or B. What does that sentence saying? The mass flow rate of the hot fluid is twice the cold. Is it A, correct mathematical statement or interpretation of that, or B? All right, you ready? Let's take a look at how the class voted on this, because I think if we can't get the right mathematical representation of some of the information, we're doomed, true? But we're not 100% correct, are we? We're pretty close. So why is it that this is the correct statement? Maybe try it. Try some numbers. Let's say I'm saying that the mass flow rate of the cold is 2 meters cubed per second. or let's not do meter cube, that'd be a volumetric flow rate, kilograms per second, right? What would then be the hot? Would it be 4 or 1? If the hot fluid is twice the cold fluid mass flow rate. If this is an example, e.g., some example, for example, the mass flow rate of the cold, if it's 2 kilograms per second, wouldn't the mass flow rate of the hot be 4 kilograms per second? Wouldn't it be twice the cold? So B is the right answer, isn't it? All right. Now, what happens when the mass flow rate of the hot fluid goes up? What does the red temperature profile do from your experience with heat exchangers? It kinks up a little bit. It slopes up. Does something like that, doesn't it, as the mass flow rate of the hot fluid goes up? Is a higher heat capacity rate. There's a lot more fluid flowing through the hot side. So what happens here, you have to make this observation. The big key observation is the temperature of the cold out is equal to the temperature of the hot in. Why? The heat capacity rate of the hot is greater than the heat capacity rate of the cold. Make sense? Yeah.
I kind of got confused on that because I made it to where the temperature of the hot out is equal to the temperature of the hot in.
Well, that would be if this went to infinity. If it went to infinity, the hot out would be the hot in. But guess what? The cold would still only go out as the highest that it could go out, which is the hot in. Yeah, if you said that m dot hot went off to infinity. All right. So I think a little sketch like that helps organize the thoughts. Okay. Then we go back, we say Q out of the hot is equal to Q into the cold. Is that a true statement? And I see a lot of people wrote it down, and I'm glad. I think some of the first people wrote it down got the answer correct quicker. All right, so then we say, well, it's the mass flow rate of the hot times the specific heat, constant pressure of the hot times the temperature hot in minus temperature hot out equal to the mass flow rate of the cold, specific heat, constant pressure, cold, temperature cold out minus temperature cold in. That equation look good? Then we cancel these. We replace this m dot of the hot by being 2 times the m dot of the cold. So I'm going to put 2 m dot of the cold. The temperature hot in is known, minus the temperature hot out equal to the mass flow rate of the cold. Temperature cold out, I'm now going to substitute there. And I think that's where some people will get bogged down, but then oh yeah, that's it. The temperature of the cold out is equal to the temperature of the hot in, true? Minus the temperature of the cold in. Now you have everything ready to solve this problem. Okay? And so what happens when you solve this problem? What do we get for the temperature of the hot out? 75. Now, let's go ahead and take a look at grading this then. All right, go back, please. There. So 58% did well. Okay? Any questions about that one? Does it make sense? Professor, you just keep asking hard questions. Yep, here it is. I'm going to give you some time to work on it. Same type of problem. Same type of problem. But it's slightly different wording. All right, so I encourage you to make a little sketch of the heat exchanger, put 2 sides to it. This time the hot's going in the same direction as the cold, isn't it? That's the parallel flow. So the temperature of the hot in is 120 degrees C. The temperature of the cold in is 30 degrees C. And then make a plot of the temperature as a function of position X out to the exit. Now, because it's a very long heat exchanger, that we're going to put in the 30, the 60, the 90, the 120. There's 120. There's the 30. So if I know that we're going to double, we're going to have the hot fluid flow rate twice the cold fluid flow rate. But to start off, conceptually make them the same. If they're the same, what's the outlet temperature? If they're the same, mass flow rate. Well, they would be smack dab in the middle. What's smack dab in the middle? 75 degrees C. True? A lot of people I see computed that. And so the cold fluid would go from 30 to 75. The hot fluid would go from 120 to 75 on the outlet. So maybe even sketch it all the way over there. True? Because it's really, really long, they're going to come out at the same temperature. Isn't that the critical observation? The temperature of the hot out is equal to the temperature of the hot out is equal to the temperature of the cold out. Did you realize that? Yeah. Now, if we boost the mass flow rate, double it, what happens to the red hot curve? It goes up a little bit, doesn't it? Because it's doubling the flow rate. So it's going to come up like this. What does the blue? Stay in the same position? No, they got to come out at the same temperature. It's infinitely long. So actually, the cold fluid's going to come out warmer in the case where the mass flow rate, this case right here, the mass flow rate of the hot fluid is twice the mass flow rate of the cold fluid. These two cases was the mass flow rate of the hot fluid equal to the mass flow rate of the cold fluid. True? Then we get it oriented in our mind. Everything looks good. This was a critical observation. And now we just go back and say, what is the rate of heat transfer out of the hot? That always equals what goes into the cold. Always. Both cases. And so it's going to be 2 times mass flow rate of the cold, specific heat, times the temperature hot in minus temperature hot out, equal to mass flow rate of the cold, specific heat. I just substituted 2 times m dot c for m dot h there, times temperature of the cold out minus temperature of the cold in. And here you could even say, I'm just going to say that this is the outlet temperature. This is the outlet temperature because they're both the same temperature. Hot is equal to the cold out. Cancel, 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 cancel. And so the temperature of the outlet is equal to, what do we pick up here? We're going to pick up 3 temperature outlet is going to be 2 temperature hot in plus 1 temperature cold in. Divide over by 3. So it'll be 2/3 of the hot in plus 1/3 of the cold in. True? Is that the math that you worked out? Is so when you stick in the numbers, it's 2/3 times 120 plus 1/3 times, what does this equal? Isn't it 90? And you could almost have just guessed, like, look, it's greater than 75. How many people did that? It's greater than 75 and it's less than 120. There you go. It's 90. You're well prepped for the FE exam. Because usually that's what they do. They give you answers that are pretty far apart. It's above 75, but it's below 120. All right, so let's grade it. Very good. Wow. Okay. What happens to the temperature of the cold out if the mass flow rate of the hot goes off to infinity? It goes out to the hot inlet temperature of 120. Exactly right. All right, so let's press forward. Shell and tube heat exchanger having a total area heat transfer of 25 meters squared. So the area is equal to 25 meters squared. It's a shell and tube. So when you see a shell and tube, you're thinking something like this and some like that. Okay. Has 2.5 kilograms per second of engine oil entering at 60 degrees C. So the mass flow rate of the hot is 2.5 kilograms per second. It's engine oil. And the temperature hot in is 60 degrees C. And the mass flow rate of the cold, which is 10 kilograms per second, and it's water. And the temperature cold in is 10 degrees C. The overall heat transfer coefficient U is equal to 1,000 watts per meter squared Kelvin. Determine three things. The rate of heat transfer, that's Q, we'll probably want it in watts. The fluid outlet temperatures, the temperature of the hot out in degrees C, and the temperature of the cold out in degrees C. So those are the three things we want to solve for. Should I give you a second, or you just want to see me solve it? Just see me solve it? Okay. Are you given the temperature hot out? No, that's what you're asked for. Temperature cold out? No, that's what you're asked for. Basically, you need to use the effectiveness NTU method. You solve a few of these problems. That's the strategy here. We're going to use the effectiveness NTU method. So in the effectiveness NTU method, you're going to say to yourself, I know a few of these equations. Probably the equation I need to get to is saying Q is equal to the effectiveness times Q max. And how am I going to get the effectiveness? I'm going to look for a function of the number of transfer units. How do I get the number of transfer units? That's UA over C min. And then I start checking. I say, hey, they're giving me U, they give me A. I need to get C min, then I can get N to U, then I can get the right correlation, get the effectiveness, then get Q max, etc. All right, so a couple steps that really could be a different order. Let's try this. Let's calculate C of the hot. Well, it's going to be the specific heat of the oil times the mass flow rate, m dot C sub P of the oil. And I didn't leave enough room, so let me do this. I'll make some room here. I'm going to go to the table and I'm going to get the specific heat of oil. But at what temperature? You have to say it's not going to be at 60, it's going to be lower than 60 degrees. Maybe I pick it to be average around, I don't know, 40 degrees C. And then I'll get a specific heat of 1951 joules per kilogram Kelvin. And then I can get the heat capacity rate of the hot fluid. The heat capacity rate's 4878 watts per Kelvin. All right, get the specific heat of water, about 4190 joules per kilogram degree C. I have to assess, well, what temperature is it going to come out? Maybe it comes out at, I don't know, 30 degrees or 20 degrees. So if I assume that it has an outlet temperature, I don't know, a little over 10, then I just get the specific heat. It's slightly temperature dependent. Heat capacity rate of the cold fluid is going to be 41,890 watts per Kelvin. So of these, which is our minimum, C min is 4878 watts per Kelvin. What's Q max? It's C min times temperature hot in minus temperature cold in, which the Q max for this problem comes in at 243,875 watts. All right, I get the number of transfer units, UA over C min. Here's C min, there's U and A, and so the number of transfer units is 5.1256. So I know number of transfer units. I need to calculate the ratio of C min to C max. And the C min to C max is 0.1164. So these are the two critical pieces to allow me to get the effectiveness. I can get the effectiveness either graphically, if I have that available to me. It's not going to be that accurate. Or I can get it with an equation. So we have a shell and tube. I'll assume it's one shell pass. They didn't really give that lot of information. Put in C sub R and NTUs, and you can calculate the effectiveness with this equation to be about 0.937. Let's take a look at by plot. Here is by plot. What was our NTU? A little over 5.1 something, 5.12. So it's right in this vicinity. What was the ratio of C min to C max? It was quite low. the ratio was about 0.12. So this is where it's 0, so it's really hard to read, but you assess, oh, the effectiveness is quite high. It's around, they have it a little too high, I think. It's around right in the middle, right? This is 0.25, that's 0. 0.12, it's right around the middle, and we're right around there. So it's effectiveness about 0.94. What did we get from the equation? 0.937, 0.94. So now we can go back, and we had the effectiveness 0.937, and you calculate then the actual, the product of the effectiveness times Q max, and we find that it's 228,474 watts, and so that would be the answer for part A, or one of them. And then what about the outlet temperatures? The temperature of the hot out, temperature of the hot in minus Q divided by the heat capacity rate of the hot fluid. So we calculate the temperature of the hot out, 13.2 degrees C. Likewise, the temperature of the cold out. Temperature of the cold out is 15.5 degrees C. This was a pretty straightforward problem, I hope. I think I spent too much time on the other two questions. Does it look good? You did something like that, no sweat? All right. So we did that. We see a lot of cross-flow heat exchangers. You pop the hood, you look at your radiator in the front of the car. What type of heat exchanger? Is it shell-end tube? No. Concentric tube? No. It's really cross-flow. So you have a manifold, either top or bottom, and the flow goes liquid water mix, ethylene glycol mixture, either flows left to right or right to left, sideways or up and down, depending on your radiator. And then the air flows the other direction, cross flow. And if you ever look inside, they're usually not round passages, or more like oval passages for the water to flow. But what happens over here, they have fins, right? It's fin surfaces to help promote heat transfer. So here, both fluid streams would be unmixed, meaning that once it's between these fin passages, it stays, and it doesn't sort of go back and forth between them. And once it's in this tube, it stays in that tube, and it doesn't go and jump between tubes, so it's unmixed. So when you look for an illustration, they'll put lines like this saying it's unmixed in that direction, it's unmixed in that direction, so you'll have a cross-flow heat exchanger with both fluids unmixed. You can get analytically the effectiveness NTU relationship plotted, or you can sometimes find an equation. In the textbook, they give it to you where the effectiveness is a function of NTU for this heat exchanger. Do they give NTU as a function of effectiveness? No. So you would just have to root solve or iterate to if you needed to go that direction, or use the graph. But here is the effectiveness as a function of NTU. In a cross-flow heat exchanger, it's used to cool air using cold water. So we have air, and we don't want that air to be heated. The air is going to be cooled, and you put water in the other side. So maybe I put it like this, water, going like that, water. So what is the cold fluid if the air is being cooled by the water? The water's the cold fluid. What's the hot fluid? The air. All right. Water flows on the inside of the tubes and air on the outside of the tubes. Very, very common. Fins are used on the air side to promote heat transfer on the air side. However, the overall thermal resistance is still dominated, even if you put fins on it, it's still dominated by the air side. Write the equation for U. Can you write the equation for U, the overall heat transfer coefficient? That's exactly it. So 1 over U is the way I would normally start to write it. because it's a resistance, and you have sum of resistors. And you have a resistor 1 over H on the, let's say, air side, area on the air side. That's a total finned area. This is the convection coefficient, and you have some overall efficiency. And then you have some resistance due to fouling, if you had it. You'd have some resistance due to the wall, resistance due to fouling on the water side. This is the air side, water side, plus 1 over H on the water side. Let's say it's inside. H inside, area inside. Now, what do you think about the fouling? They didn't give us any information about it, so you would neglect it. What about the wall resistance? The wall, through the tubes. No, and the conduction through the fin material is actually embedded in the effectiveness of the fin surface. So now also it says right here, what is this key thing? The overall resistance is still dominated, even after you add fins on the air side, it's still dominated by the air side. So what about the thermal resistance on the water side? It's negligible. So guess what? So U is simply the overall fin surface efficiency, the overall area of the fin surface, and the convection coefficient on the air side. That's very, very common. Very, very common. Well, looks like I'm out of time.